Just get started. All right, so it's a great pleasure to introduce our next speaker, Alex Hock from Oxford University of Oxford. Topological recursion, insertion objects.
Yes, hello, and thank you first of all for the invitation and for being here, and it's great to be again on a conference. So here's I actually thought I should talk on Thursday, and my talk should then be related to other talks, but now I try to say something before we know it, and before we learned about it. So I will talk about functional relations, which are within topological recursion for the X and Y symmetry. This is the symplectic symmetry or symplectic transformation, which Elba actually want to talk about, related to higher order free cumulants. And I computed the same functional relation with other techniques, which called loop insertion operator. There are probably certain problems of the existence of this loop insertion operator, but that should be clarified, and I try to work on this. Okay, so first of all, I try to summarize topological recursion, even though we don't know yet what it is. So I hope most of you know topological recursion in general, and I will work here with the genus zero spectral curve. So it means that I just give you some rational function x and y from C to C. In the notion of topological recursion, you would talk about coverings of Riemann surfaces, but it's easier here, just stick to x and y, some rational function from C to C. And I built my omega 0, 1, 0. So this notation is different from the usual notation you find in topological recursion on Wikipedia, for instance. So I denote the superscript as the genus and the first subscript as the number of points or the number of boundaries of my surface. And then, and then I define omega 0, 1, 0 as being y dx, and omega 0, 2, 0 as the usual Bergman kernel, as it's called. It's for a genus zero spectral curve of this form. And then I say that all omega gn 0, which we know from TR, are just given by topological recursion. So this is a picture of topological recursion. I will not write down the formula of topological recursion because I don't need it. But the idea is essentially that you have your omega gn0, as I call it. It's given here on the left-hand side, which is given by some kind of kernel, which cuts out a pair of pen. This kernel is built from omega 0, 1, 0 here and omega 0, 2, 0. And a rest with which is in this case omega g minus 1 n plus 1, 0. So it has one topology less, let's say. So in the sense of the Euler characteristic. Plus you can have another splitting where you cut out this kernel here. Again, a pair of pens. And then you sum over all possibilities of this kind of topologies and this kind of topologies here, where the prime here means that you don't count the topology G is 0 and just one boundary here. And the I1 or I2 is the empty set. So, I mean, this formula is completely fine. And what you do in topological recursion is then that you take the residue. So there's a residue formula where you sum over all residues at the ramification points of X, and you compute W, G, and 0. So the ramification points of X are probably some chalk here. So just to be complete, so x prime z is equal to 0. So this defines the ramification point at z, where this is fulfilled. And yes, and then I go further and just invert the situation. Just change completely the role of x and y. And what happens? You define omega 0, 0, 1 to be x dy, omega 0, 0, 2 to be the same as here. Again, the Bergman kernel. And then I say all omega 0 m's are generated by topological recursion, where we interchange the role of x and y. So the same formula where you build the kernel by this omega 0, 0, 1 and this omega 0, 0, 2, which is the same as here in the uppercase. And you take this formula of topological recursion with the residues at y prime of z is equal to 0. So at this ramification point y, where this is fulfilled. I mean, because it's then easier, first of all, because otherwise, if they are not rational, you can have higher genus spectral curves, and then you have to fix certain cycles because they're living on a genus G surface, for instance, and you have to fix certain cycles, for instance.
So if I just say x and y
why not? I mean, meromorphic. I mean,
I'm just trying to figure out what you're making right now.
Okay.
What is it that you're summing?
In this sum here.
Yeah. So what are the actual?
I mean, this omega GNs. Okay, I don't want to be. These are differential forms, first of all. Oh, yeah. That define this condition here, that G1 plus G2. So, I mean, you sum over G1 plus G2 equal to G. The set I1 and I2, which are disjoint sets, sum to I, where I is from 1 to n, index set. Omega G1, I1 plus 1. Then you have here some Q, where you take the residue over Q going to this ramification points. And then you have the set I1, G2, I2 plus 1. And then you take here the Galois involution, whatever it is. I will not talk about that because I don't need it. And yes, except the case where GI is the 0 and the empty set. And then I exclude the case where GII is equal to 0 in the empty set. Just this special case. It's not a sphere because here's still one boundary here, still some variable. So it's, the sphere was one boundary. Okay, yeah, okay. I forgot to say that these omegas are differential forms, multilinear differential forms, and they are generated by topological recursion with this formula. Okay, and the spectral curve is then built by these two functions x and y. So you can put one function into the other. You formulate a polynomial, which is written as e of xz and yz. This is a polynomial of a certain degree, and this polynomial gives you a curve in the algebraic geometric sense. It's a complex curve, which is of genus 0. This is the important point here, which is my assumption that I have a genus 0 spectral curve. And because I have this rational parametrization of this curve. And then it's known that this kind of spectral curve depends on certain moduli. So these are the Kontsevich times. So if you have in mind the Hermitian one matrix model, these are the parameters of the potential and so on. So this curve depends on certain moduli, so certain moduli which you can vary. And then since you write this polynomial in this way, you can locally try to figure out what capital X of y is, where you say that small y is now to be hold fixed with respect to this moduli. Or you can write capital Y of X, where you say small x is fixed with respect to the moduli. And this you can make locally for X. So you have a formal expansion capital Y of X here. So, and then I have this kind of picture in mind where you have here the Z space, and then you map with X of Z to the X space, where on this space I say I fix X with respect to this moduli, or you can go to the Y space where you fix Y with respect to this moduli. And you can go from one space to the other, and they are formally inverse to each other. Okay, next we define the correlators. So these correlators are typically of interest in some combinatorial problems. In the Hermitian one matrix problem, these are the resolvents, and you compute this the enumeration of maps. So, and they are defined as W, G, and 0 in my notation of X of Z1 or X1 of Z1. So this was the rational function X multiplied by dx1 Z1 up to dxn Zn will give you omega G and 0. So these W's here are also, you can see them as formal expansions within Xi. And for the WG0M, you do the same with the dy's here. Okay, and then in particular, we have the case where W010 is given by Y of X and W001 by capital X of Y. This was because omega 010 was just Y dx, and then you see that directly. And whenever I write small letters now, X and Y, I think them to be fixed with respect to this moduli I told you before. So there are this notion of this moduli, which you can vary. Your spectral curve depends on this kind of moduli. And I assume that small letters are fixed with respect to this moduli. And then there exists a loop insertion operator. Probably is not completely rigorous, and for on kind of spectral curves, completely clear that it exists. But it should be somehow be there somewhere. And I guess in most of the models, you can write it more explicitly down. In other models, it's not clear how it looks like. It's not really probably constructible. But the idea of this loop insertion operator is the following, that you have an operator dx acting on WGN0, and it gives you a WGN plus 1, 0. So for the spectral curve with xy, you just add 1x here. And for the same, we can do it for y. So we have d tilde y on WG0M, which gives you WG0M plus 1. And you add some y here at the last point. So, and then this insertion operator actually is defined by a variation with respect to this moduli of the spectral curve. There's in the paper of Enel how they define it. And they have to fix here all the x's with respect to this moduli, and then you can define this spectral curve. And in this way, this is also well defined. But I also assume that dx of small y is 0 and d tilde y of x is also 0. So it means that I can choose this y or here this x to be independent on the moduli where I take the differential, this operator acting on it. So actually here, I talked to Gaetan about that, and he said he has a problem with this formulation, but I could somehow argue why it will give actually similar or the same result at the end if we define it differently. But I mean, I don't think I have enough time to explain that. So this differential operator, this loop insertion operator is a derivation. It satisfies the Leibniz rule and the chain rule because it's a variation with respect to some parameters. And this will be the only tool I will need to compute these functional relations.
Sorry.
Yeah.
You say derivation is some algebra. So what is the algebra?
Yeah, the algebra of functions, yeah, of formal functions. So you have this formal expansion and the coefficients of the, so this W are formal power series in the x's, and the coefficients of them are related or given by this moduli. Okay, and then the interesting or the important step here was that I can define intermediate correlators. So I call them W, G, and M now. So we make no sense if N and M are not, or if one of them or both of them are not 0. What does it mean? So I define them by dxn of WG n minus 1M acting on this expression, or by d tilde ym on this expression. And the calculation later will show that this one is equal to this one, so this is well defined. So up to now, this is of course, why should both give the same result? Why should the left-hand side be well defined? But actually, if we can define it in this way, we see by combinatorial explanations later that they are well defined, and actually this means that this operator commute in this way how I wrote it here. Yeah, the loop is just one additional boundary. I mean, if you have this picture here at the beginning in mind, this was just one additional boundary which you add. So if you act with the loop insertion, I mean, these are the omegas here. But if you act with the loop insertion operator on this object here, you have one additional boundary. Okay.
That means have a surface.
Yeah. Yeah, you do something like puncture. This is the picture you should keep in mind. Yeah. And then, but what happened if we have this formal expansion W, and we say that one of its variables depend again on the formal expansion? What happens then? So let's just compute by Leibniz and chain rule that the operator acting on W and M gives you a W n plus 1M, as it usually do. But it also acts on this variable here, where you take the derivative with respect to this variable. I wrote here then y tilde at the, inserting at y tilde is equal to capital Y of X times the operator acting on Y of X, where Y of X was by definition W010, and this gives you then W020. So this is then a different action if we assume that one of these variables is itself a formal expansion. And what we can also do, which is more complicated, but yeah, okay, maybe I mentioned it here. But usually, if you have this loop insertion operator, dx, it can just act on something which fixes all the x's with respect to the moduli. So actually, if you you can also have this expansion, and you can take this as a definition, which is then Wn plus 1m g xn x. Oh, this is different x's, sorry. X tilde n plus somehow sum over, let's say, k from 1 to m d over d, let's say y tilde k w n m g x1 up to xn y tilde 1 up to y tilde m at where the y tilde i's are given by capital Y of xi times w0 to 0 x k x. So you can also take this as a definition if you don't want to define the operator here with this additional condition. Then you can take this as a definition. And you can then do the same for the tilde operator and say also that this, or you prove at the end that these two functions generated in this way are the same. Okay, this is what I wanted to mention. Okay, but now consider an example. Let's compute the cylinder correlator, W011. So the cylinder correlator was defined by the action of dx on capital X of y, or by d tilde y or capital Y of x. And capital X and capital Y are formal inverse to each other. So we can write it in this form formally, that we have small capital Y is given by small y, sorry, is given by capital Y of capital X of y, where now capital Y depends on this moduli. So we take the operator on capital Y as well as on capital X, but not on the small y. So on the left-hand side, if you act with dx on the left-hand side, it's just 0. And then you compute on the right-hand side the action, which is the action on the capital Y, gives you this term. Or you have to take the derivative of y with respect to its argument times this operator on capital X of y, which gives you W001. And then this inserting is just here, this derivative of capital X of y. So you can bring it to the other side, and then you form this one, this one. So you have W011 xy is given by dx of y by dy, and here just by the Bergman kernel again. Okay, we can go one step further. Let's, or you can do first of all the same by acting with d tilde y on x on this function, and you see at the end it's the same result. And what we can then do is we can move to this z-plane. So we insert for x just x of z1 and y of z2, which means that capital Y of x is y of z1, and capital X of y is x of z2. Just insert it here, and you see that both expressions are actually then again the same, and this is then an expression on this z-plane if you want. So you pull it back to the z-plane where you have this result. But we can go even one step further. Let's compute the pair of Pann's contributions. So 0, 2, 1. We act with dx2 on the previous expression, which yields on the left-hand side just W0 to 1. So you add another x here. And on the left-hand side, it commutes with the derivative with respect to y. Then it acts on the capital X of y, or it acts on the W0 to 0, where it acts either on this function w or on the variable of it, which is again a form power series, or on this thing here. And you compute everything and expand it. At the end, you find that this thing gives you a derivative of something, which gives you actually a derivative of W011, where you insert again this function, and also here the same, insert again the previous relation, and then you find that you actually can pull out one global derivative in this term. So it's not obvious that you can pull one derivative out here. And this W030 just by an action on this function here. So this is not so trivial that you find something. So two different terms generated here and generated here, which is actually have a primitive, if you want to say. So where you can no, this was wrong. Where you pull out the derivative. Yeah. So moving to the x plane, we can, this was the comment also to this remark here. If we have dx2 on W0, 1, 1, where I move everything to the x plane, will give at the end the same result. So we can play with this definition here, the same game. It just generates more terms which cancel but give the same result. So we can also do it with a different definition. This is just what I want to point here out. And now I want to go to the general formula for W, 0, and M. And for this, I need some notation, some graphs, some trees. And it seems quite weird that I introduce here these trees, but they will be important in the later formula. So I want to find now, where is it? There it is. I want to formulate for W, 0, and M the functional relation depending on W0 and 0 just. And for this, I define the following trees, which is a connected tree, T, with N, I write it down here, N square vertices, M round vertices, and some black bullet vertices. So we have 3 different types of vertices. Then they are labeled from 1 to N. They are labeled from 1 to M. Then the black vertices have valence greater or equal than 2. The square white vertex has valence 1. And we say that just black and white vertices are connected. So whenever I have a black vertex, it's just connected to white vertices. So either to this one or to this one. And the black vertex can have any valence bigger or greater than 2. Also, the white round vertices can have any valence greater or equal than 1. So any valence. And then I associate to the jth round white vertex the number rj of t, which is the valence. So they have the valence rj of t. So the jth vertex of this valence, and the black vertex is uniquely classified by a double set ij. So this is the double set ij. So this is the black vertex, which is connected to some round vertices, which are further connected, and to some square vertices. They are labeled here by, let's say, I1 up to IN, and this is J1 up to JM, and then the set I is given by I1 up to IN and J by J1 up to JM. So this double set says to which white round vertices or white square vertices the black vertex is connected. And this set, calligraphical I of T, is just the set of these double sets for 3T. Okay?
White vertex joined by
You can have this one connected through a black vertex of valence 2. Yeah. Yes. This one is always a leaf. Yeah. Yes. So then I gave some examples. Oh, sorry. Here, some examples. So the set G21. So it has 2 square vertices, white square vertices, and 1 white round vertex. So you have either this case where you have 1 black vertex or 2 black vertices. Or the set G12, where you have 1 square vertex and 2 white round vertices. So these 3 different cases. or the case G31, where we have 3 square vertices and 1 white round vertex. And here you have 3 possibilities. Either k is equal to 1 or to 2 or to 3, because here you don't distinguish if this is 1 or 2 or 2 or 1. So this consists of 5 trees. Okay, so any other question of trees? And then one specific example is the set Gn1, where you have 1 white round vertex and n square vertices. And this is classified by the following case. So it's isomorphic to, let's say, the situation where you have a set of sets, I1 up to Ik, where k is the number of black vertices. And you look at all these sets where I1 up to Ik, the union of it is given by the set 1 to n, and you divide by some permutations because you don't want to overcount. So it means
that's a partition, what I was calling a partition.
yes.
Okay.
This is for this specific.
And you don't care about order of blocks?
Yes, I don't care about the order of the blocks.
Yeah, just like partitions, you don't.
Yeah.
Blocks aren't ordered.
Yeah. And this is just the example of Gn1 because we have this white round vertex. And yeah. 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 So, and as you can probably imagine, if you look at arbitrary GNM trees, it's much more complicated. So even the number of these round vertices makes it very complicated. So the leaves are quite easy. The white square vertices. And then there's a technical lemma that you can reconstruct Gn plus 1m from the set GNM by connecting to a tree in GNM. So we add here this n plus 1 means adding a white square vertex labeled by n plus 1. You can add it in 2 different ways. And you sum then of all different ways you can add it to all trees. So we add it either to a white round vertex through a black vertex of valence 2, which is shown here. Or you can add it to a black vertex directly. So, and if you take the set of all trees and you sum over all possible ways to add it to a tree, you get the next set, Gn plus 1m. Okay, this is something you have to prove. Just by construction showing that by this construction that any tree inside here is uniquely, and all of them are generated and any of them are uniquely generated. So, and then you can also construct the set GNM plus 1, where you add now a white round vertex labeled by m plus 1, either again to a white round vertex through a black vertex of valence 2, which is this case here, the same case as here, or you need to connect it somehow to a black vertex, but because your white vertex can have any valence, it's much more complicated now. So, and the reason how it's built, it's that the new vertex, the white round vertex, you connect to a black vertex, where how you connect it is classified by the set GK1. So you either split this black vertex or leave it and connect it. So this is the first where you have just 1 block, or you connect it through 2 blocks or 3 to n blocks or to all k blocks. So this is how you construct this Gn plus 1, GNM plus 1. Okay, this is also what you need to prove. And then the next step is I define a weight on the set of trees. So I say that the ith square vertex is we associate a variable xi to the j's round vertex, a variable yj, and then we associate this weight. So it's quite, it seems weird to associate that kind of weight to it, but it makes sense, hopefully, why we need it. So here we have the valence of the jth round vertex, and you take the derivative with respect to rj minus 1 with respect to this yj, the variable associated to the jth round white vertex. Then you take this product of dxyk over dyk over all white vertices, white round vertices. And this double set classifying as black vertices gives you a W0 I plus j, where you take the cardinality of them, and then 0 and xi, and capital X of yj. I hope this makes sense. I have one example, because otherwise it's quite weird, just to state it here. So let's look. So we have here 4 round white vertices and 2 square white vertices. And the first one has valence 3. So we have to take the second derivative associate with respect to y1. Here we don't have any derivative, so we have somewhat the 0th derivative. Here we have also the 0th derivative. Here we have the first derivatives with respect to y4. Then we take the product of all dx, yk, with respect to dyk. And then we have to look at the black vertices, where we have the first black vertex is connected to 2 white round vertices. This is why we wrote capital X of y1, capital X of y2. The second black vertex is capital X of y1, capital X of y3. This vertex is of valence 3. So we have W030, which is connected to 1 white square vertex, which is the x1 here, and to capital XY, because it's connected to this one, and capital X of y for this one. And the last one is W020, because it's connected to x2, the square white vertex, and the round white vertex, capital X, y4. So does this example make sense for? Good. And now the theorem is that the functional relation between all W0 NMs is given by the sum over all trees G and M of this weight. This is the theorem. And in particular, if we look at W00M, which where we take n for 0, we just have to sum over all trees G0M of the weight. And this 0 here means that we don't have any square vertices. We just keep the round vertices, so the complicated vertices. And this formula here coincides with this formula of Borot, Charbonnet, Garcia-Falde, Light, and Chardrin, where they compute for free probability, for higher free probability, the relation between all this, between all the functional relation. And okay, how does the proof work? So the idea of the proof is, of course, to proceed by induction in m plus m. So either we go to the set Gn to Gn plus m with this operator dxm plus 1, or Gn to Gn plus 1 by d tilde y of m. So we act with this differential with this loop insertion operator on this weight or on this weight, and where the weight was defined in this way. So it either acts on capital X of yk, or it acts on the w, or it acts here with a derivative on the w, but then afterwards on this capital X. So it acts on the red and on the blue part. So the first situation where we include one more white square vertex is that you act with your loop insertion operator dxm plus 1 on this part here or on this part, which gives you then a W020 if your dxm plus 1 act here, or on the x of yk, let's say, or I choose the j here. And then you see that you can pull out again a global derivative. A global derivative means that your white vertex. So it means like you have an action on this white round vertex, which means that you have a global additional derivative. So you have one more valence. Instead of valence r, you have now r plus 1 because you have one more derivative, one global, which you can pull out and connect it through a black vertex, which is given by w020 x n plus 1, which is given here, and x yj is given here. Okay? Or you can have the action of dxn plus 1 on this function, which is just connecting this white square vertex to the black vertex, which is just adding to the previous function xn plus 1 here. And then the lemma I stated before said that these both cases together generate the whole set gn plus 1m. This is then the proof here. And for gnm to gnm plus 1, it's a little bit more complicated. So the first case is again the action on the xyk here and the xyk here, which gives you at the end w020 with one global derivative and one additional term of this form. So we have again the action here on the white round vertex, which gives you a white round vertex in formula, and this part gives you a black vertex, and this part gives you then that here you have to insert capital X of yj. But the more complicated stuff is if you act on the w function, which gives you then first of all the w xi capital X of the yj's, where you have this vertical line ym plus 1. So you have first of all generated this function where you have not a 0 here on the right hand side. But we know by induction this function is actually given by all the trees inside gi plus j1, which is essentially given by all these different cases we argued before. And also then here the lemma guarantees that you generated everything exactly once. And this is then somewhat a proof. But what we can do with this w, g, and m's, or just for 0, I said, we can then define an omega g and m, some kind of intermediate forms of topological recursion, which are then given by just multiplication of dx z1 up to zn, dy z1 tilde up to zm tilde. And we pull them back on the z plane. And then we have, for instance, this relation for omega 0 nm, where we divide here by dy z1 tilde and so on. Just, I don't want to write them here at the end. And then we sum again over the trees, and this formula a little bit simplifies here, where we have a product of a dx z tilde j's to the power of this valence of the vertices and so on. So this is the result for TR then. And in case of n equals 0, you can actually run then topological. I mean, let's say n is equal 0. You have xy as your starting point and yx as your step. Then you compute all 0 and 0. And here you compute with TR omega 0, 0, m. And then you can try this formula and look if they are related exactly in this form. The point is that, okay, I have not mentioned it, but all these forms generated here have poles at the ramification point of x. These forms have poles just at the ramification points of y. So we relate something, if we set n equal to 0, something which has just ramification points of y to something which has just ramification point of x, where all the poles at these ramification points of x have to vanish. And but the formula holds, yeah. Okay, and then yeah, I had to include some additional thing because I guess Elba will talk about that tomorrow. She will talk about this triple duality. So this symplectic invariance, this XY symmetry and topological recursion is here, where this functional relation in most of the cases holds with what I showed you. And fully simple maps and ordinary maps are an example of topological recursion, where the duality between fully simple and ordinary maps is given by the same relation of just interchanging x and y. And from fully simple and ordinary maps, you can construct higher order the relation to higher order free probability and to free cumulants, and they should satisfy the same functional relation, what they proved in their paper. So it means that the WG0 and WG0M have this functional relation, but furthermore, what I tell you is that here on this two examples, we can even give a canonical way or a canonical definition of W0NM. So this intermediate correlators, where you don't have one of them to be zero. And probably something like that should also exist. I don't know, in free probability, where you have generating series of a mixture of cumulants and moments. I don't know if this makes sense, but if they should probably satisfy the same functional relation. So just to summarize everything, so starting from WG and M generated by topological recursion with XY and WG0M generated by YX, I try to make a canonical definition by loop insertion operator for WG and M. And this functional relation holds for all W0NM, where depending on W0, K0, where K is smaller or equal than n+1. This result coincides with the result of the paper of Elba and its collaborator. And what I have not mentioned, the weight I defined is for genus 0 equivalent to their weight, but it's much easier. So I had to simplify their weight in the case of genus 0 to see that they're actually equivalent. So it's probably an easier way to compute it. But to go to higher genus, you need first of all the functional relation between WG10 and WG01. So because loop insertion operator just gives you an additional puncture. So you need first of all this relation. And I don't know if, I mean, I can take it from their paper, but it's so complicated, the formulation. But in principle, I guess this procedure will hold and work there as well, where you go from trees to graphs. So the graphs will then have a genus, or the Betti number 1 is then somehow the genus, or you can associate also a genus to the vertices, to the white and to the square vertices, to the black vertices, sorry, because the black vertices are related to the correlators. And yeah, what does this all have for implication is that it relates fully simple to ordinary maps, where we have n ordinary boundaries, m fully simple boundaries. So this WNM means for maps that I say I have n ordinary boundaries, m fully simple boundaries, and I relate them to just ordinary boundaries, or just fully simple if you want, whatever you want. And then the question is if this has also canonical definition of generating series in higher order free cumulants and moments. I don't know if you can have that as well. That would be interesting. Yeah, thank you.
Thanks very much. Questions or comments?
Yeah, please.
So at the lowest level, there's that formula that I ended.
Yeah.
Is that somehow your case that curve going? So there's some connection. But UE, there's got to be a spectral curve, right?
You mean for the Gaussian unitary ensemble? I think for the Gaussian unitary ensemble, you mentioned it is just the Wigner semicircle law, I guess, right? Will come out. I think it's just something like probably x is given by z plus 1 over z, and probably y is the same. I think it's probably the same. So, but this is actually a problem. Okay, I forgot something to say at the beginning. I had to assume that X and Y have different ramification points. And probably in this example, it will not hold because then the ramification points are the same because the functions are the same.
The lowest order R function RZ. So that would be, that X would be the K function.
Probably this is the then the spectral curve. I don't know. It can be worked out.
So I mean, the inverse satisfies the quadratic equation. That would take the inverse of that function.
Yeah.
Z is the function of X.
It's a quadratic equation. If you put Y here inside.
That would push form
Yeah.
of the semicircle form.
Yeah.
Which satisfies a quadratic
Yeah.
equation.
Yeah, probably this would be the spectral curve, where you have X is given by times some constant, typically called gamma. And this constant depends then on some parameter T, on this moduli then. And yeah, you can run this game, but because here you have no ramification point, right? It means that from this, so from X, Y, I compute all the W, G, let's say, N zeros. And from Y, X, I would compute all the G, 0 M's, which are actually 0 for negative Euler characteristic, because they have no ramification point. Because all this topological recursion stuff needs a ramification point. So it means that this functional relation, this formula here, for instance, or the theorem, let's say, here for what do we want to have? N equals 0. The left-hand side is just 0. So the right-hand side sums together to 0.
Yeah, I don't know. It doesn't really make sense.
Okay.
It'd be interesting to see if what all of this comes out.
Yeah. Yeah, because yeah, the Gaussian ensemble should be somehow the simplest example of everything. Yeah. Yeah. So there are also higher order free cumulants.
That's right. Yeah.
Up to which order? Up to 3, 4?
Okay. This is the Zaghi paper where they did all of F1 GN.
Yeah. Okay.
But I think what happens, they're all 0. Everything is 0 except second order. The second first order is 1.
Yeah.
Maybe that's what that 0 is on the right.
Maybe yeah, it's really yeah.
But it's true that all of the higher order chickens are 0.
Yeah. I mean, yeah. We'll be at least consistent.
It's not the only.
Yeah. Yeah, as long as one of these functions is just a linear function, it means that all the sum of the right hand side should count, yeah, should sum up to 0. Yeah.
Is that also what you get? Voiculescu transform?
That's right, yeah.
Right?
That's the map, yeah.
Voiculescu.
Yeah.
For flow.
One more question there?
Yeah, that's precisely. Okay. Is it possible to say one has a topological? Okay.
I mean, the functional relation Jamie showed, where you have this C1, probably you call it, and M1. One of them is then your capital Y of X, and the other one is then the capital X of Y. This is somehow how they are related. So this initial data, this X and Y, is related to them.
Okay. So
Probably where you have to take, I don't know. Yeah, probably this is then something like X of Z, and this is then something like y of z, something like this. And then you have a certain relation. Yeah, I mean, it's, yeah, you have to, I mean, you cannot see the relation. I mean, the relation is very specific to free probability. And in topological recursion, you have, I don't know, this functional relation probably for all x and y. And also for this specific case. Then. Yeah.
That's very reminiscent of some probability though, like where take permutation, multiply it by transformation, when you split a cycle in two, or you join cycle.
Yeah.
And almost all the formulas come from that operation. Either splitting cycles by multiply it by transformation cycle, or taking elements which are in different cycles and multiplying by circles, just join circles or split circles. Everything by splitting, joining together in a combinatorial way.
But you can do it also for the moments, for the generating function of the moments, and for the generating function of the free cumulants. I mean, this is actually the idea here, right? That you do it on both things. That you do it here and here with the same operator. So let's say you have an operator which acts here and one operator which acts here. So you need one operator which gives you one more, or the next higher order cumulant, generating function of cumulants, and also the next moment. But with this operator, you can also act here or here.
I mean, I can't, I don't know. I'll borrow two circles, like one circle today, tomorrow two circles. And I don't know how to do three circles.
Yeah, I mean, that's the point already at 3 circles. So at W03, it's very complicated, and you need this intermediate. So in my example, intermediate function W21 to see how it works.
Yeah, I mean, I haven't seen that correspondence. Or I don't know. But it typically, I have a couple of examples. Look at the sequence of numbers.
Yeah.
Otherwise, there's no way to guess how that things go.
Another question. It's the word question. Constraints come from like the sort of constraints.
Yes, I think Gaetan will talk about that. Gaetan in his mini-series that actually probably this loop insertion operator comes from, but they are coming from Virasora constraints.
So it's a bit like the sort of constraint, but the higher version.
Yeah, probably. You have to ask Gaetan. He knows everything about that. Yeah, let's hope. But yeah, there's a relation to.
Yeah, it's here from. Okay, so before we finish, let me make at least 2 announcements. First of all, the good news: we'll have wine and cheese after the last lecture today. So it's downstairs. So the second one, the resident speakers will get office. So Asker will give you access. So if you want to stay overnight here,
we have to. Get those talks ready.
That's right, just in case.
Just in case we don't want to go home.
And the third one, for lunch, we'll go. I mean,